Not on this paper, I should say, but we worked together for a few years after Patrick finished his PhD at Stanford, and he has since moved on to NYU. And I can't say enough good things about Patrick, and so I guess we'll let his talk speak for itself, if that's okay.
All right, thank you. That's perfect. So today I'm going to talk about fitting method for hierarchical models generally, but with a specific focus on recommender systems. So if you haven't seen recommender systems, the basic idea is that you have a large group of users and a large group of items, and you somehow have to figure out what items to recommend to what users. And this shows up all the time, but most prominently in online shopping applications, or let's say you go into Netflix, they have to decide what movies to recommend to you, and so on. So to make things concrete, I'll be thinking of movie recommendations. And you get some data. The data looks like this. You have a set of items which correspond to movies. You have some information about each item. So it has a numeric ID, has a title, and one covariate indicating the genre of the movie. You have a collection of users, in this case roughly 70,000 users. You may have demographic information about the users, but in this data set you do not. And then you have some information about past behaviors of the users. So you'll have something like ratings. So a list like as follows. Here, a list of user rating movies. So the first rating here, user 36072, rated movie 21, and they gave it 3 out of 5 stars at this particular date and time. Then they rated movie 47, they gave it 5 stars, and so on. And we have 10 million, roughly, ratings in total from which to learn things about the user's preferences and the movies. Okay, so there are 2 general strategies to this. One is called content-based, the other is called collaborative. Content-based is you figure out what types of movies the user likes, and then you recommend movies of those type. So you know this user has watched a lot of action movies and they tend to like action movies. Well, maybe you should recommend action movies to the user. Collaborative, on the other hand, is recommending based on items similar users have liked. So, you know, I like a certain set of movies. Patrick Wolf also happens to like those same set of movies. And then there's an additional movie that he likes that I haven't seen yet. Maybe I'm going to like that additional movie as well. So that type of recommendation is called collaborative filtering. All right, so content-based recommend items based on their attributes. Collaborative recommends based on the behaviors of similar users. Okay, so it turns out if you use a hierarchical model, you can use both strategies simultaneously. And so I'll go into this in more detail in a little bit, but the way I'm going to think of it is I have some user rating of movie J, Yij. I think this is related to user-specific tastes, which are encoded in a coefficient vector beta I, and movie-specific attributes, which are encoded in a covariate vector xij. And then there's an additional population structure. I think that if I took all the coefficients for all the users, they come from some larger population, in this case normal with some mean mu and covariance matrix sigma. All right. And so in the late 2000s, late 90s, early 2000s, a few people recognized that if you use such a model for recommender systems, you could simultaneously use the collaborative filtering and the content-based recommendations. So let me go into a little bit more specifics. It's a little abstract right now. I'm going to take all of the data for a particular user I. And so user I has made, say, ni ratings in the past. I'm going to store these in a vector yi. Okay, so they rated one movie and they give it a 5. They rated another movie, they give it a 3. Another movie, they give it a 5, and so on. At the time of the ratings, there were some covariates for each movie. And those I'm going to encode in this feature matrix X. So this movie that got rated a 5, it was a drama, and it was relatively popular, and the user had not their most recent rating was not positive. Okay, so focus specifically on these first 4 variables, which include the drama or the genre of the movie. This encodes something about how popular the movie is, and this encodes something about what kind of mood the user's in, if they're in a good mood or a bad mood. Okay, and if you know the features and I know the user's tastes, then I can predict the rating. And so how is this content-based and how is this collaborative? Well, okay, so I'm going to say expected rating conditional on beta I, conditional on the user-specific coefficient vector, is a linear function of the features and the coefficients. And this part of the model allows me to do things like the following. I can say, okay, user I likes action movies. Movie J is an action movie. Therefore, we should recommend movie J to user I. So how does this work? The statement user I likes action movies, that means that the entry of beta I corresponding to action is large and positive. Movie J is an action movie. Well, that means that the entry of X corresponding to the genre for action is 1. And we should recommend movie J to user I. Well, when I do this dot product, it's going to be positive and large. Okay. Okay, so in this way, I'm recommending, or I'm predicting the tastes based on the attributes of the movies. And please stop me at any time if there's questions. Okay, what's the other part of the model? That's the hierarchical part. So I think these user coefficient vectors beta I are coming from, say, some normal population with mean mu covariance matrix sigma. When I have this part of the model, I can do things like the following. I can say user I likes action movies. Users who like action tend to dislike drama. So we should assume that user I dislikes drama. Okay, so how would this work? So user I likes action movies. So this user has watched a lot of action movies in the past, and our estimate for beta I, the action component of beta I is large and positive. Let's say this user has never watched any drama movies in the past. So we don't have any information about their coefficient for drama. But if we happen to know that action and drama are negatively correlated, so if this sigma here encodes a negative correlation between the action coefficient and the drama coefficient, then learning that the user has a large action coefficient tends to suggest that the user has a negative or small drama coefficient. Okay, so we'll use data to estimate parts of beta I, and for the parts of the components that we don't have information, we can use this covariance structure, which we've learned from other users, to fill in those missing elements of beta I. Okay, so in this way, we're getting these collaborative, this collaborative information.
So Patrick, it's collaborative in the only through the X's. It's collaborative up to a point in that you don't get a lot of information about beta I. So if the regressors are fairly low dimensional and people watch a lot of movies, would you still call it collaborative?
So traditionally, when people talk about collaborative filtering, you match on the X's, or maybe match on the Y's. You say, okay, this is one user's Y vector, and this is the other user's Y vector, and you look for similarities there. And so I will give you that this collaborative filtering is not fully general. There are other forms of collaborative filtering that this would not capture. But what it is capturing is what the associations are between these tastes beta I. Those get filled in from the other users. Yeah, other questions? Okay. Okay, so again, content-based, so you use the movie attributes and the user tastes for those attributes to predict the rating. And it's collaborative in that the components of beta you don't have much information about can get filled in using this covariance structure. And this covariance structure is something that you have to learn from data. Okay, so the problem with this is that you can't, up until recently, just could not fit one of these models at commercial scale. So a lot of people in the late 2000s said it just couldn't be done. You know, maximum likelihood, Gibbs sampling, you know, no matter what you're doing, they say, okay, you can't use one of these models if you have a large amount of users or a large number of ratings. Okay, so why is that? Well, okay, most common methods for fitting such a model, EM algorithm, Newton-Raphson, or profile likelihood. All these methods have a high initial cost, so you do a bunch of matrix factorizations to start with, proportional to capital N, the number of ratings. And then after that, you do some iterative process. The cost of the iteration scales with capital M, the number of users. And these methods require, you know, many, many iterations. Typically, when you add up all the costs, it just becomes prohibitive very quickly. So the data application I'm talking about today, number of users is roughly 100,000. Number of ratings are for 10 million, and I'm using a small number of covariates, 10 covariates. You can use these algorithms to fit with this data set, but it takes, you know, many hours to do so. If you go to like a real commercial scale application, these numbers are going to be even bigger, and you just won't be able to fit. Okay, so there are two more recent approaches for fitting models at large scales. One idea is to split up the data set into parts, fit a separate set of parameters on each subset, and then do some sort of averaging to combine the parts. So if you had capital K equals 10 processors, I would divide my 10 million ratings into 10 sets of 100 million each, 10 sets of 1 million each. I'll fit a separate model on these smaller data sets and then do some sort of parameter averaging. If you do this, it'll cut the amount of computation time by a factor of K, the number of processors. This does not reduce the total amount of computation, but it will allow you often to scale such a model to a larger data set. So I'm going to compare against this method later on. Another popular approach is to use stochastic gradient descent, especially popular in the machine learning community. The basic idea is to so if you write down the likelihood, it involves an integral over the beta i's, integral over the randomness. So the idea is to treat the beta i's not as random variables, but as fixed quantities. This gives you something called an H likelihood. And then maximize that using stochastic gradient descent. Advantage of this is it's often much faster than maximum likelihood. Disadvantage is that there are typically some tuning parameters involved, so you need to do some sort of regularization typically. And if the number of parameters is comparable to the number of data points, this will sometimes be inconsistent, where integrating over the betas would not be inconsistent. Okay, so what I'm going to talk about is a different approach based on moment-based estimation. The idea is to split the data into capital M chunks, one chunk for each user. Use these user data in isolation to get user-specific coefficient estimates. And then use these estimates to do some moment matching and estimate the parameters of the hierarchy, estimate that mu and that sigma matrix. The advantage of this is it is not iterative, and it's very easy to parallelize. Disadvantage is this is no longer maximum likelihood. There's potentially some loss in statistical efficiency. So I'll spend most of the talk going into the details of this procedure. Okay, but just as a comparison against these other approaches, so the moment-based approach, you still have a high initial cost. You still have a relatively high cost per iteration, but there's only 2 iterations. So that results in big savings. And often in practice, the dominant cost is the iteration, not the initial cost. Okay, so just to demonstrate this, I took the movie lens 10 million data set and I fit hierarchical models to subsets of the data set of varying sizes. So I looked at 100 ratings, 1,000 ratings, 10,000 ratings, 100,000, and so on, all the way up to 10 million ratings. And then for 3 different algorithms, I'm showing you how long it takes to fit a hierarchical model. And so LME4, this is probably the most popular R package for fitting such models. You can see a scaling roughly linearly in the sample size. To fit the full 10 million rating data set takes about 10 hours. For stochastic gradient descent, it also appears to scale linearly in the sample size. If you include the cross-validation time required to choose the tuning parameters, it also takes a full 10 hours to fit. If you don't include the cross-validation time, it still takes more time than the moment-based approach. The moment-based approach, interestingly, as you increase the sample size, starts to plateau in terms of computation time. But if I plot versus the number of groups, the number of users, then I see that linear behavior instead. So the moment-based approach scales, in this example, not with the number of recommendations, it instead scales linearly with the number of users. Right? And at the largest sample size here, it takes about 10 minutes to fit versus 10 hours for the other methods.
Patrick, the scaling you just mentioned, is that entirely consistent with this? If you step back one slide, so can you, which is dominating here?
So this is dominating. The reason it's dominating is, so how it works is you take all the data, you split it up by user, and then for each user you basically fit a separate estimate.
Okay.
So due to data locality, once you've split it up by users, it typically just scales with M.
Gotcha.
Okay, so remainder of the talk, I'll go into some more details of how this procedure works. I'll show you some theoretical results and showing that it's consistent and that gives you estimates that are asymptotically normal, and then I'll try to convince you that it actually performs well in practice as well. Okay, and by the way, this is not a new idea. You can trace the origins of this procedure that I just described back to Cochran in 1937. So Cochran was doing this with one parameter. His motivations were more like meta-analysis. But basically, it's a similar idea to what I just described. Then he had a few more developments until Swamy in the 1970s. He's an econometrician. He extended this Cochran's idea to more than one parameter. So p greater than 1. Carter and Yang was also a similar extension. Cox and Solomon extended that to nonlinear models. All of these, why wasn't this enough? Why couldn't I just take Cox and Solomon and then run with it? All of these procedures assume that the user-specific design matrices, the XIs, have full rank, which seems innocuous, but when you have a large scale application, it quickly breaks. So what does it mean for the design matrix to have full rank in the case of a movie application? Well, that means every user has to have watched at least one of every genre. If you didn't have that to be the case, then the XI would not be full rank, and you would not be able to use these existing methods. So a large part of what I'm doing is extending these methods to the cases where you have rank degenerate design matrices.
And was the connection already known in the sort of collaborative filtering or bi-clustering community, or no, because your models are slightly different?
So the connection between collaborative filtering, content-based filtering, and hierarchical models, that has been known since 2000.
Yeah.
So, but nobody has used these models because they weren't able to fit them.
I gotcha.
Yeah. You had a question? No. Okay. So, basic idea is compute user-specific coefficient estimates, estimate the population parameters by matching moments. Okay, so how does this work? I'll start with the full rank case. So assume this user design matrix Xi has full rank. My model is that the user ratings are equal to Xi times beta I plus error. Okay, so what I'm going to do is I'm going to get a user-specific coefficient estimate. Here's just the least squares estimate. What are the properties of this this estimate bi? Well, its expectation conditional on beta I is equal to beta I, and so its unconditional expectation then is just equal to mu. And the covariance of this vector bi has two terms. One is from the population structure here, and the other is the estimation variability. Okay, so just looking at the slide, you can see, okay, when all the xi's have full rank, if I wanted to estimate mu, an obvious thing to do would be just take the average of all the bi's, right? That's an unbiased estimate for mu. And if I wanted to estimate sigma, I could take the sample covariance of all the bi's, subtract off some bias term, and that would give me an estimate for sigma. So what I've just described is basically Cochran's method and multivariate extensions thereof. Now, things get a little hairy when the x does not have full rank. So now I can still do least squares. I'll use a pseudo inverse instead of a regular inverse. So I'll get a bi, x transpose x, pseudo inverse x transpose y. But now if I use this pseudo inverse, it's not a unbiased estimate of beta I. Basically what ends up happening is that there are directions determined by x in which you get information about beta I, and everything orthogonal to that, you get no information. So if I've only seen action movies, it's possible that my expected action estimate is unbiased. But if I've never seen a drama movie, the best I can do is sort of estimate 0, and that's going to be a biased estimate of the true coefficient. Okay, so but there's still information about mu in this bi. So what I'm going to do is I'm going to choose a weight matrix that kills the directions orthogonal to the row span of x. Okay, so basically I'm going to choose a matrix that puts weight on directions where there's information and 0 in directions where there's no information. And if I do that, then I can be guaranteed that the expected value of wi times bi is equal to wi times mu. Okay, so if I choose the weights such that they are, has the same null space as the xi, then this equation will hold. And a similar equation for the covariance.
When you're talking about expectations, you mean you're averaging over both the randomness of the user I's choices and the hierarchical model.
Yes, yes. And so, yeah. Right, so the basic, a single BI gives me just a little bit of information about mu, but if I average a whole bunch of BIs, what does the hierarchy tell me? That beta drawn from normal, mu, sigma, that tells me if I average a lot of beta i's, I'll get a mu.
Without giving anything like, is the strategy here to get some estimate of the parameters describing the heterogeneity of the betas, the betas i's first, and then your second step is then to adjust these bi's?
Exactly. That's the basic program. If I knew the mu and the sigma, then I could get posterior estimates of the betas.
Right. So the general story in hierarchical modeling, you have if you integrate over the beta i's, you have some very small number of parameters, but it's computationally difficult, and the task is to get those parameters in the hierarchical model.
Right. Exactly.
And then once you have those, then it's just combining. Right. Okay.
Right.
Using
Right.
base rule.
Yeah. Exactly. Okay. So yeah, once I have the mu and the sigma, I can sort of shrink all the betas towards the mu, shrink them more when there's less information, and so on. Okay. So looking at this equation specifically, this suggests an estimator for mu, which is I'll take a sum of wi times bi, and then multiply by some inverse matrix, and that'll give me an estimate of mu. So specifically, my estimate of mu hat is going to be, I'll add up wi times bi, and then I'll multiply by the inverse of the sum of all the wi matrices. And if I do this, then I'll have an unbiased estimate for mu. And then for the sigma, things get a little hairier. Then you use weighted covariance. So this is like a weighted sum of outer products. There's still an equation relating the expectation of this quantity to sigma. It involves some Kroneckers and so on, but doing a similar moment matching trick, you can get an unbiased estimate for a sigma. Okay, so then, like, how do I choose these weight matrices? Well, the optimal weights, the ones that minimize the variance of the estimators, depend on the unknown population covariance matrix sigma and the noise variance sigma squared. And if I knew these two things, then I can compute this wi. This would minimize my variance for the of mu hat. So what we're going to do instead is take some initial guess for sigma and sigma squared, run the moment matching procedure once to get an initial estimate of sigma hat and sigma squared hat, and then plug those in again and run the whole procedure over again. So doing this is two-step procedure. In principle, you could iterate this, but it turns out to be sufficient to just do 2 steps.
Sorry, Patrick.
Yeah.
So for different xi's, they may have different ranks, right?
Correct, yes.
And does this guarantee different wi's have different ranks?
Yes. So in general, wi will have the same rank as xi.
Wi has the same rank as xi, but I guess you have a term in your mu hat, which is a summation of a different wi.
Right. Yeah.
What's the dimension of wi?
So they all have the same dimensions, but they have different ranks. And it's basically like you take the right singular vectors of x, multiply that on the left and the right, and then put something in the middle. And so that's exactly what this is doing here. So the ui and the ui transpose are the right singular vectors of x, I, and then this thing in the middle is rank by rank.
So, do different xi has different number of columns?
Yes, but this is still going to be a p by p matrix. wi is still going to be a p by p matrix. So the middle part in the brackets, square brackets, is going to be rank by rank. And then ui is p by rank. So everything.
You're missing a curly brace after your more Penrose inverse.
Oh, thanks.
Try to figure that out.
Yeah. Okay.
This is biometric ordering braces, right?
Well, missing.
Yes.
Okay. So yeah, compute these user-specific estimates. That takes the scaling proportional to the number of ratings, and then matching them, the weighted moments, is what scales with M. Right, computing these estimators mu hat and sigma hat scales with M. Okay, so that's, and then like Peter was saying, once you have the mu hat and the sigma hat, then you can shrink using empirical Bayes estimates for the individuals. Okay, well, I'm going to talk about the population parameters. So first result is that these estimates are consistent. And there's a whole long line of technical conditions. But basically, if the user-specific estimates have finite fourth moments, you don't need to assume normality of anything. You can guarantee that the estimates of mu and sigma have an error that scales with the smallest eigenvalue of the sum of the weights. So basically what you need is you need a number m, the number of users to go to infinity. And you also need that if you look in any direction, that the amount of information you have in that direction also goes to infinity. Yeah.
Sorry, what is that? User-specific estimates have finite fourth moments?
So unconditionally, expectation of BI to the fourth, or norm to the fourth, has to be finite.
That doesn't come straight from the model, or are you not
So
assuming?
you don't need to assume
Because
normality.
you're doing this without assuming the normality.
Right.
Okay.
Your mu hat had a flavor of a sort of importance sampling, so I was trying to understand if your omega 1 inverse is somehow related to the variance of the the variance of the weight, the WIs in some sense. I mean, I can see it's the minimum direction energy or something, I guess, right?
Yes, so like what would happen if you had one particular WI going up that is infinite and the others are bounded, and you end up putting all your weight on one particular,
variance
and
of
then,
weights
and,
goes crazy and you're dead.
and then you don't get anything
Yeah.
consistent. So that somehow comes out in this bound. The bound is like very messy, so I'm sparing you the details. But if you're interested, I can.
I was just thinking there's all these sort of practical tricks from the importance sampling literature that, people compute the optimal weights that depend on unknown quantities, and then you do something else in practice, and there's all kinds of interesting strategies about that, which could have a practical effect, but not for the theory. So.
Yeah, so like choices of weights, yeah, there's a whole bunch of details like that the paper goes into more. But basically what you want is you don't want any particular WI to outgrow all the other WIs.
Yeah.
Otherwise you don't get this averaging behavior, and you don't get this law of larger numbers. Yeah. So, but the basic idea all follows from the estimator. For the mu, this is a fairly straightforward result. You can compute the variance of mu hat. It turns out the covariance matrix of mu hat is this omega 1 inverse. So as long as that goes to 0, then you'll get a consistent estimate. For the sigma, things are much more messy, but there's still a consistency result. All right, so next result is that these estimates are asymptotically relatively efficient. So what do I mean by that is, I can consider two estimators. One where I use the optimal variance minimizing weight, the other where I do this two-step procedure. Take an initial guess, get a preliminary estimate, get new weights, get a second estimate. So it turns out this two-step procedure, when you compare it to the optimal weights, the difference is negligible as long as the same conditions for consistency hold. Okay, so this is much more subtle, but basically you do a Taylor expansion of these estimates, and you show that perturbing the sigma and the sigma squared a little bit does not change the estimate too much. So as long as you have a consistent estimate, everything is okay. And then finally, final theoretical result is that these estimates are asymptotically normal. So that is, if I scale mu hat minus mu by this sigma 1 to the 1/2, I get something that's multivariate normal, mean zero, identity covariance. And so same consistency conditions, but you also now need that you have a large M. And this is just a Cramer-Wold device and central limit theorem, so fairly standard. Okay, so just to recap of these results, we have consistent estimates. These two-step estimates are asymptotically relatively efficient, so as good as if you knew the optimal weights. And these estimates of the mu are asymptotically normal, so we can do things like get uncertainty quantification. All right. Actually, before I move on, any other questions about the theory? Okay. So just in simulations, here's a simulation for a hierarchical linear model. I'm comparing a bunch of methods. So LME, LMER, these are two standard R packages for fitting hierarchical models. This LMER.split is I split the data into 10 parts, fit a separate estimate on each part, and then combine them. This is the proposed procedure, moment hierarchical generalized linear model, and then the last is stochastic gradient descent. And so what you notice here, so here I'm plotting how long it takes to fit the model to a particular set of simulation parameters as a function of the sample size or log of capital N, so log of the number of ratings. And what you can see is that the moment-based procedure is faster than these likelihood-based alternatives. It is slower than stochastic gradient descent. Yeah.
So are they giving the same estimates?
No, so there's a cost of this, right? So how do they do in terms of prediction performance? So the likelihood-based procedures, so LME and LME-R are both different maximum likelihood procedures. And the moment-based procedure are performing similarly, especially for large sample sizes. This split combined strategy is giving worse prediction performance. And stochastic gradient descent is giving really bad prediction performance. That is, you would like this to go to 0 as.
On the previous slide, was the split combined, was it faster because you're using, I mean, that's the total computation.
So this is total computation
Right,
time. So yeah, if you want to do parallel computation time, just divide this by 10.
Right now, go to the next page and you see that that still doesn't do it.
Right.
Yeah.
I didn't
So
understand the last slide.
This
Split
one?
No, the previous one. So split was the worst. This idea of splitting is to make it.
So this
But he
is
didn't divide
serial
by 10.
computation time. So
Oh.
so this if you have 10 process, but the reason I'm doing serial, if you had 10 processors, you could do the moment-based procedure in 1/10 of the clock time as well, because you split your data into different chunks for each user, fit a separate estimate on each user. So
Well, wait, without getting the degradation on the next slide in performance? So
yes, you
The
could get.
moment would have no degradation, but split combined does.
So split combine. So I'm comparing serial computation time.
Right.
I'm saying you will get exactly the same estimates, quantities, no matter how many processors you use for the moment-based procedure. For the split combine, the more processors you use, the worse performance you
Thank you.
get. Yeah.
And there's overhead.
Okay. So yeah.
So I don't understand. So as the number of samples, presumably all these procedures are consistent. So as the number of samples increases, they should be giving you similar estimates. But now you have the prediction is diverging, it seems. And so, I mean, are you not dividing by the number of samples or so, or what's going on?
So for these likelihood-based procedures and for this procedure and for so these first four procedures, there are consistency results.
Yeah.
Right? And you see that prediction performance here. Here's various other things: fixed effect, random effect covariance, and so on. Right? These are all doing well. So like this is the log of the loss, right? And this is all going to
I see.
0.
I see.
As a function of n for all of these procedures. But for the stochastic gradient descent, this is based on H likelihood. There is no consistency guarantee there. And you're seeing this empirically as well.
Right, but it's a little surprising that it doesn't improve at all, right? That it doesn't work at all.
Well, I mean, this is a case. So stochastic gradient descent doesn't estimate a full covariance matrix, full P by P covariance matrix. It estimates a diagonal covariance. So it's possible the degradation is coming from that.
So what is your statistic for prediction?
This is just like,
I thought prediction high would be good.
so this is
I didn't see
loss.
the y-axis.
So it's like squared error loss
Okay.
between the expected value of y and the predicted value. But this is like squared error loss between the mu and the mu hat. There's a covariance loss, like trace of sigma minus sigma hat dot with itself. Random effect, this is summing over all the beta i's, beta I minus beta hat I, and then the prediction which I just showed.
Anyway, Patrick, your moment thing is spot on MLE.
Right. So this in a linear model, yeah. So that's good news, right? We're getting basically in the linear case we have faster by a factor of 10, and prediction is basically the same. So I also looked at a logistic regression, hierarchical logistic regression, and here for computation you have a similar story. So the moment-based procedure is faster than the likelihood-based procedures, slower than stochastic gradient descent. But if you look at prediction performance, now there's a cost that you're paying. So the moment-based procedure is this purple curve. For small sample sizes, actually outperforming maximum likelihood. And then for large sample sizes, it is performing worse than maximum likelihood. Now, okay, so why is it doing better than maximum likelihood? Well, for logistic regression, I'm not actually, so I have to split up my data into user-specific chunks, get a separate estimate for each user, and then combine everything together. Those separate user-specific chunks, I'm not getting by maximum likelihood, because if I do maximum likelihood with logistic regression, often that's not going to exist. I'll have separation between the classes. My maximum likelihood estimate is infinite. Then I won't be able to use this procedure. So what I'm doing instead is using a penalized estimate, a penalized likelihood estimate for the moment-based procedure. I'm using Firth's modified score, which reduces bias, and in small samples outperforms maximum likelihood. So that's why this moment-based procedure is giving better prediction performance for small sample sizes.
Why does the likelihood go up first?
I think this is like an early stopping. So I don't know, I think that has to do with the optimization routine. And I think there's some tolerance, and initially,
It doesn't converge sometimes?
yeah, I think in these cases, like the likelihood.
It can happen with logistic regression, how iteratively we do these scores that just won't
Yeah,
converge.
that's probably what's happening. LME is doing this iterative procedure. All right, and yeah, so other error performances, you see similar behavior. The moment-based procedure is doing better than likelihood for small samples, worse than large samples, but in terms of time, it's better. Okay, so now let's go into practice. Back to this movie lens data set. So remember, this is what I started the talk with. There's 10 million ratings, 70,000 users, 10,000 movies. I have predictors. Genre is a categorical variable with 4 possible levels. Item popularity. So what I do is I take the 30 most recent ratings for a movie. I take the log of number of positive ratings versus number of negative ratings, and user mood indicator of whether or not the user liked the last rating. If you fit this with GLMER, it takes you 10 hours. If you fit this with the moment-based procedure, it takes 10 minutes. This used to take 30 to 40 hours, and then they released a new version of the software. So now I have to put 10 hours. And I'm going to use a logistic model. I'll try to predict whether or not the rating is positive or negative. Where positive counts as a rating of 4 or 5, negative is rating of 3 or below. And so some users have 10 ratings, some users made 1,000 ratings. Average number of ratings per user is 140. Okay, so these are the predictors I mentioned. Okay, so now let's see. These are the coefficient, empirical Bayes adjusted coefficient estimates. So I got a separate coefficient vector for each user. I use those coefficient vectors to do some moment matching and get the mu and the sigma. And then I go ahead and readjust the coefficients, get a posterior mean. And so each dot here corresponds to a user and their coefficient for these particular variables. And so we can see, for example, that the users who have a high comedy coefficient tend to have a low children's coefficient. The users who like children's movies tend to dislike action movies. The users who like popular movies tend to like children's movies, and they tend to dislike action movies slightly, and so on. So we can see there are some associations between these user-specific coefficients, these user-specific tastes. Next thing you would be interested in is, what's the misclassification? So if you try to predict positive or negative, how well do you do? If you use a hierarchical model estimated by this moment-based procedure, you have 28% of the time you make the wrong prediction. If you use a model with no shrinkage, so each user gets a separate coefficient estimate that's computed in isolation from the rest of the data, then the misclassification rate is 29%. And if you just fit one logistic regression model and get a single beta and use it for all the users, then misclassification rate is 32%. So these differences don't look very meaningful, but it's a little more interesting if you drill down by how many ratings the user has made.
Patrick, sorry, just remind me that there are 5 ratings they can make, right?
So
1 through 5.
I've coded 4 and 5 as positive and 1 through 3 as
Okay.
as
So
negative.
when you train on this binary converted response, and all the misclassification is also from that.
Right, correct. Okay, so here there are 3 curves. So I've segmented it according to user. I'm showing you prediction performance. So for the users who've only made 10 ratings, the best performing model is this hierarchical model. Then the global model, which uses a single logistic regression for all the users, is second best, and then the worst is this local model. For users who've made a lot of ratings, so users who've made, say, 100 ratings, the moment-based procedure does the best. Then this model that gets a local estimate for each user in isolation does second best, and then the global model does worse. And at the other extreme, the moment-based procedure and the local procedure perform comparably. So this is what you want to see. This hierarchical model is interpolating between the global estimate and the local estimates in such a way that it's always outperforming both. I'm showing you this for the moment-based procedure. If we use the other procedures, the maximum likelihood-based approach or even the SGD approach, they all do very similarly to the hierarchical. Okay, so this is basically the talk. So this procedure is fast, it's theoretically sound, and it works in practice. There's also an R package that you can use, and it has the same syntax as LME4. So you say, here's my response, here's my fixed effects, here's my random effects, and so on. What I didn't go into in today's talk is what if you have different fixed and random effects. The theory handles that, and the package handles that as well. Since I uploaded this to Cochran, there are some people in industry who found this package and started using it. The main benefit to them is that since this fitting procedure is so fast, it really enables exploratory analysis for these hierarchical models. So it can change your fitting time from 5 hours to 15 minutes. When that happens, you're at much more liberty to experiment with covariates. And in particular, I've been working with these people at a clothing startup, and they have found this procedure to be really useful. Okay, so thank you.
More questions for Patrick? More questions than we've already asked?
So, so how is it gonna work when you have, for example, you think of the movie lens data as like matrix type of thing, and you want to have some sort of movie popularity in there as a random effect as well, right? So I can see how you code it in your syntax, because I've coded this thing before in LME4, so you put it in a random effect for the movie, but that seems like it would create a pretty horrible design matrix.
Yeah, I think what you're saying is like you want some crossed effects. So this, you want one random variable for the user, another for the movie,
right.
and maybe the user parameters are from some population and the movie parameters are from some other population, and then you have these cross random effects. So when you do that, I don't know how to fit the parameters. Art Owen has worked on that a little bit.
But it seems like I don't know how you did your coding, but it seems that you can specify that if, for example, in LME4, when you just say you have, you have your outcome and it's a person-movie pair, and you have.
Yeah, so in LME4, you would have another term here that's like plus 1 bar movie. And then that would, so that, if you do that here, it'll say, sorry, I don't know how to do that. So, but what I did instead on this data set is I said, okay, I can't have a movie popularity random effect, but what I can do, these, covariates can depend on recent behavior. Yeah. So rather than have a random effect for each movie, I'll just take an average of the 30
Sure.
previous ratings, and then everything goes through fine. I'm using like partial likelihood instead of full likelihood, but everything goes fine.
So at the end of the day, you split 3 and 4 stars that are, was it 4 and 5 into?
4 and 5, yeah.
So did that correspond to like and dislike, or that's just a way of dichotomizing?
So that's, fairly standard, fairly common way of splitting 1 through 5 into just 1, 0. But it was an arbitrary decision. So,
Yeah, I mean, different users may have really different scales.
Yeah.
To look at all at how many, some people have a whole lot of 5 stars and some have a whole lot of 0 stars.
It does have a person-specific random intercept, right?
Yes.
Yeah.
Yes.
So you're getting that to some extent.
Anyway, from a money-making point of view, you're the business school guy. But you don't have to do a better job on the ones who've done a lot, because they're already using the thing. It looked like you only had a 1% improvement in classification,
right.
but if it's all in the one where they're up for grabs, that's where the big deal is.
Yeah, exactly. So like these numbers here are driven mostly by these
Right,
users.
but those are already sold.
Yeah.
Because they've been on it for years, and those guys over there, doing a little bit better for those is where the money is.
Right, exactly. Yeah.
Excuse me, I have a related question about censoring. So in movie categories, there is quite a bit of censoring because it's really dependent how you choose these categories. So how this kind of errors, in which models these errors affect better those?
So I'm not sure if I understand what the censoring is. You're saying that.
Misclassification of the categories. So for instance, if you choose rules wrong at the first instance.
Yeah. So if these covariates are like somehow meaningless, like there's some random errors in the x. This whole model is conditional in the x, so I wouldn't. There's no like trying to adjust for that. But in such a situation, and presumably the betas for those genres would be close to 0. Yeah.
And another question, so you assume the static distribution, yeah? So that the user's characteristics don't change in time, yeah?
Right, yes.
Did you try anything with when you kind of allow this?
No. So that's another case like Peter mentioned. So now you're saying you have a user-specific random fact beta that changes over time. I don't know how to do that.
It's not going to improve computation time.
Yeah, exactly. So the what enables this whole procedure is that for each random effect beta, you can get an independent set of data and use that independent set of data to estimate that beta. If you start having things evolving with time, it becomes much more difficult, and if you have crossed effects, then it's not possible to portion out your data in such a way where it's all independent.
Well, I think the cool way would be like system dynamics approach or something like this, because with respect to beta, to the extent you consider this kind of population averages, and if you kind of model the average person and then you take from there the betas, so this would be kind of cool approach.
Okay, yeah, that might be the case.
Any final questions before we thank Patrick? All right,